Look around you. Whether you're in a crowded city or a quiet field, the laws of physics feel stable. Gravity pulls down. Light moves fast. Entropy increases. And if you could step into a spaceship and travel hundreds of millions or even billions of light years in any direction, modern cosmology promises something very specific. On the largest scales, the universe should look, on average, the same. This idea is called the cosmological principle, the assumption that the universe is homogeneous and isotropic. In plain terms, no preferred places, no preferred directions. There's no cosmic north, no up, no privileged orientation. Everything should be statistically uniform. But what if it isn't? Over the past 2 decades, our best telescopes and satellite missions have hinted at something deeply unsettling. In the faint afterglow of the Big Bang, in the spin of distant galaxies, even in the arrangement of structures billions of light years across, we keep detecting signs of a pattern, an alignment, a possible cosmic axis. If that axis is real, the universe may have a preferred direction. And if that's true, our most fundamental assumptions, from the nature of the Big Bang to how we model dark energy, could need revision. Today, we explore that possibility. This is the story of the potential preferred direction of the universe, a phenomenon some cosmologists call the axis of evil. To understand why this is so shocking, imagine standing in the center of a perfectly calm, infinite ocean. Whichever way you turn, north, south, east, west, the horizon looks the same. That's isotropy. Now teleport thousands of miles away. The view is still the same. That's homogeneity. For nearly a century, cosmology has relied on the universe behaving like that ocean. Small-scale differences exist, stars, galaxies, clusters, but scale out far enough, and things blur into a smooth cosmic mist. Then we captured the first detailed baby picture of the universe. The cosmic microwave background, or CMB, is the oldest light we can see, radiation from just 380,000 years after the Big Bang. It's almost perfectly uniform, interrupted only by tiny temperature fluctuations. Those fluctuations seeded every galaxy we see today. When NASA's WMAP satellite mapped the CMB in the early 2000s, cosmologists expected randomness, no special directions. And broadly, that's what they found. But on the very largest angular scales, things weren't random. Patterns in the CMB seemed to align along a single axis. Researchers Kate Land and João Magejo called it, half as a joke, half as a warning, the axis of evil. Not because it's sinister, but because it threatens the simplicity of cosmology itself. So the immediate reaction was caution. Maybe it's contamination from the Milky Way. Maybe a processing error. Maybe pure coincidence. But then came Planck in 2013, a more precise mission. And the alignment didn't fully go away. The universe appeared, at least faintly, lopsided. If there really is a cosmic direction baked into the universe, it shouldn't just appear in ancient light. It should show up in the galaxies themselves. Think about a spiral galaxy, a rotating disk of hundreds of billions of stars. From our viewpoint, it may appear to spin clockwise or counterclockwise. In a perfectly isotropic universe, the distribution of spin directions over the sky should be about 50-50, with no preferred orientation. But several surveys, including Sloan Digital Sky Survey data and citizen science work from Galaxy Zoo, reported possible spin asymmetries. In some sky regions, galaxies appear to rotate one way more often. On the opposite side, the reverse. And intriguingly, some alignment results line up with the same axis present in the CMB anomalies. This result is actively debated. Some analyses find it, others weaken or erase it after adjusting for observational bias. But if real, it's like discovering that trillions of cosmic coins don't land heads or tails evenly. They're slightly biased in one direction. Scale that imbalance up across billions of light years, and you have tension with the cosmological principle. Then came something bigger, literally. In 2021, UK researcher Alexia Lopez identified what she called the giant arc, a structure of galaxies and gas stretching across the sky for over 3 billion light-years. That alone challenges expectations. A second feature, the Big Ring, was later reported, also on staggering scales. These structures may or may not be single coherent objects. The science is still developing. But they exist near or beyond the scale where the universe is expected to smooth out. Instead of uniformity, we see features. And once again, some analyses hint they may align with large-scale cosmic axes. So what could cause directionality in the universe? One possibility, bubble universe collisions. If inflation spawned multiple universes and another universe brushed ours in the first fractions of a second, the imprint could remain, a cosmic bruise stretching across the CMB and the large-scale structure. Speculative? Yes. Impossible? No. Another possibility, anisotropic inflation, early universe expansion that wasn't perfectly uniform. If space expanded slightly faster in one direction, even by a tiny margin, that directional fingerprint could persist today across tens of billions of light years. There's a more modest idea, too, that our observable universe is just one tiny region of a much larger cosmos. We see only what light has had time to reach us. Our patch might simply be statistically unusual, like looking only at one stripe on a giant beach ball. The larger pattern may be symmetric. We just can't see beyond our cosmic horizon. Now consider motion. The Milky Way, along with the entire local group, is moving through space at roughly 1.3 million miles per hour relative to the CMB. This motion is partly due to gravitational attraction toward dense regions like the Great Attractor and Shapley supercluster. But there's also a massive underdense void behind us, the dipole repeller, effectively pushing us away. This, by itself, fits standard physics. But when paired with reports of large-scale dark flow, galaxy clusters apparently drifting toward a common direction, the question deepens. Are these local quirks or fragments of a deeper cosmic orientation? We must be precise. None of these anomalies alone is definitive. But taken together, CMB alignment, galaxy spin asymmetry, giant arc, big ring, large-scale flows, they form a pattern of discomfort, a set of whispers suggesting that the universe may be less symmetrical than we believed. Not proven, not dismissed, a puzzle. If future surveys, like the Vera Rubin Observatory and upcoming space telescopes, confirm these alignments, cosmology will face one of its biggest revisions since the discovery of cosmic acceleration. The universe may not be completely fair and directionless. It may have structure baked into its fabric from the beginning, a cosmos with a preferred direction. We were taught the universe has no axis, but perhaps it does, faint, ancient, waiting for us to notice. If you want to explore more scientific anomalies that challenge what we think we know, hit like and subscribe to Veil Origins. Here, we follow cracks in the standard model, not to escape science, but to push it. Until next time, keep your eyes on the sky, even if the universe itself might be pointing one way more than another. Veil Origins. Impossible Truths.